Difference of two squares. Recall the special product rule for multiplying the sum and difference of the same two terms. Okay, so let us review that part here. We have a plus b. We have seen this at the beginning of the other videos, and in this main topic here, this gives us a squared minus b squared. This is the type of examples that you can now apply to solve polynomials when you're multiplying in a faster method. Okay, but we have to go by steps. The binomial a squared minus b squared is called the difference of two squares. So this is difference of two squares. Okay, because a squared is the square of a and b squared is the square of b, this is known as the difference of two squares. If we reverse this rule, we obtain a method factoring a difference of two squares. All right, let's see. If we get a squared minus b squared, we can go to a minus b, a plus b, or you may want to put a plus b and a minus b. It's the same thing. Okay, this pattern is easy to remember if we think of a difference of two squares as the square of the first quantity. Notice here, the square of the first quantity minus the square of the last quantity. So let me write this pattern. Okay, it's easy to remember if we think of a difference of two squares as the square of a first, very important, first quantity minus the square of a last quantity. Okay, the language of algebra, the expression a squared minus b squared is a difference of two squares, whereas, right? So notice here, very important. So in algebra we need to be careful. A squared minus b squared is a difference of two squares, whereas, okay, a minus b squared, now note the difference, is a square of a difference, okay, is a square of a difference, not the difference of two squares, completely different. Okay, because when you expand this out, you will not get a plus a squared minus b squared. This is different than this. All right, they are not equivalent because a minus b squared is not equal to a squared minus b squared. They are not equal, so they are not equivalent. Okay, so let's see how this works out. Let's take some examples. We have a x squared minus 9. Our strategy here, let me zoom in. Our strategy here is that the terms of each binomial do not have a common factor other than 1, which we have identified at this point. The only option available is to attempt to factor each as a difference of two squares. Okay, each as a difference of two squares simply means this form. Okay, why? Because if a binomial is a difference of two squares, we can factor it using a special product rule in reverse. For example, now this problem here, this is a difference of two squares because it can be written as, this is a difference of two squares because this can be written as x squared minus 3 squared. Remember, 9 is actually 3, not negative 3. being squared. Is only the 3. Okay, now because we have this now, if it's a difference of two squares, it can be written as x squared minus 3 squared. We can match it to the rule, which is this rule here, which we have been using, which we have seen here. Okay, this rule. So let me bring that again there. We can match it to the rule by factoring a difference of two squares to find the factorization. So let's see how that works. We have here, okay, let me put this here, everything in red. So this is our working x squared minus 9. So we have a squared minus b squared. That should give us a plus b, a minus b. And this could be written as, in this case, it's x squared minus 3 squared, which is then, notice the a value is the x, so we put x, and the b is the 3, so we put here a positive 3, and then we make it here x again, and we put here a negative 3. Okay, so is a perfect square, okay, because 9, if you notice, that's 3 squared. So we can say therefore x squared minus 9 equals, right, we can have it here, x plus 3, x minus 3. You could have put the x minus 3 first if you wanted, and that's our solution. So this is the difference of two squares. All right, let's try our next example. Our next example is as follows. B, 16b squared. There is no rule to say that the square value that you will see immediately will need to be at the first. It can be at the second term. It is still acceptable. So this is a difference of two squares because why is this a difference of two squares? Because this will be written as 4 squared minus b squared. Therefore, we can say that this is actually 4 minus b and 4 plus b, and you finish there. That's it, okay, for this type of problems. But that's if you recognize it, and so you need to know your timetable. Likewise, our next term, say for example, we have n squared minus 45. Okay, since 45 is not a perfect square, this binomial cannot be factorized using integers. It is a prime. Okay, so remember what we said, right? So this cannot be given as 45. You cannot have two numbers that when you square them you get a perfect 45 unless you have like a square root sign or something like that, and we don't want that. We want perfect integers. All right, let's try our next one. So not because it looks like it means it works. So we have a squared plus 81. So this is not a okay. A squared plus 81 now we have can be written, this can be written as a squared plus 9 squared, and is therefore the sum of two squares. So this is sum of two squares. We might attempt to factor this now as to say a plus 9 and a plus 9, okay, or a minus 9 and a minus 9. Why? Because negative 9 times negative 9 will give me a positive 81. However, the following, as you can see, that when you get this multiplied, this will have a middle term with an a, and therefore this solution here, if I was to expand this out, I would end up with a squared plus 9 and 9, that would give me 18, which would give me 36a plus 81. So this is not the same thing as this, so this will not work. Likewise with this one here, if I factorize that out, I would end up with a squared minus 36a, and you end up with there plus 81. Okay, so that's 9a and 9a. Sorry about that, this is 18. Sorry about that. And this is 18. Okay, so 9a and 9a, that's 18a. 9a and 9a, but both will be negative, so we keep it as negative. So notice that we got a middle term here, we got a middle term which is not in this one here. So therefore these would not be our appropriate way of writing. It would be this one here. So this now is a sum of two squares. Okay, so I have to be careful with that part. All right, let's go with a few more examples. So more examples here, and let's say we have 25x squared minus 49. At this point you should be able to identify perfect square numbers. This could be written in the form, well, 5 is actually 5 squared x squared minus 7 squared, because 7 times 7 is 49, 5 times 5 is 25. This is now 5x open bracket squared minus 7 squared. And if we match it to our rule, we get that this is a perfect, the difference of two squares. All right, we go to the next one. Let's say we have, say for example, we have 4y squared minus 121 z squared. Now here the rule doesn't say that this must have a letter or a number and so forth, right? Just so long as you could make it as a perfect square. So what I do here is that I take the 4 and I express the 4 as 2 squared y squared minus 121 is actually 11 squared z squared. This now gives me 2y open bracket squared minus 11z squared. Okay, so we have that, and this now could be expressed as 2y minus 11z times 2y plus 11z. Okay, and as well this one here, so about that we should have expressed this also as to say 5x minus 7 and 5x plus 7. But remember guys, this you could put the 5x in the, the plus 7 first and then the negative at the second. There's nothing wrong with that part there. Okay, so let's try our next one now. See what happens to this one here. We have examples, more examples. Let's say we have 8x squared minus 8. We will factor out the GCF of m of 8 here first of all. So sometimes you may feel, oh, you know what, this 8 is not a perfect square, so this cannot be factored out if you're looking just from basic observation. But if you notice that the first thing we need to do whenever we work with problems like this is to factor out the GCF. And what's the GCF here? If you set the number 8, then you're correct. So let's see what then happens. When I factor out the 8, I end up with the 8 outside and I end up with x squared minus 1. Now that problem, this part which is inside of a bracket, looks different. This is what you could now factor out. Alright, so now the first step now here is by factoring out any polynomial which we did. That's that part there. Alright, this is not finished yet because this can still be factored out. So now the solution now will be is that this middle term here, let's pull that on the side and put x squared minus 1. This could be written as x squared minus 1 squared, which is also x minus 1 and x plus 1. All right, therefore you can put this information back here and you end up with 8x minus 1 and x plus 1, and bam, you finish with that problem there. And so then yes, it is a difference of two squares. In this case here, this inside piece, not this one here, you need to factor out the 8.